Hello, excuse me. Hello, everyone. This is Chris back again with the Ancient Scholar. Today, I'm going to continue talking about light. And the last time that I talked about in light part one, I presented this theory that one of the places light comes from, and light being a wave of light. When we talk about wave properties, and when we talk about the particle-like properties of light, which is something I haven't really talked about yet. We would call that a photon. And just to kind of recap what I said yesterday, or not yesterday, but the last discussion, is that an electron can exist in certain energy states, or what we call shells, or in-levels. And if I give that electron some energy, and it has to be a very certain amount, a very discrete amount, I can bump that electron into higher levels of energy. So at the ground state, when it's very close to the nucleus, energy-wise, it's highly bound to the nucleus. It really, it's heavily bound. It doesn't have a whole lot of energy in the sense of positive versus negative, and perhaps it's something I'll talk about a little later on, and I talk about a little bit in some of the more advanced discussions on the quantum numbers and the binding energy. But anyway, basically what we do is we give the electron some energy, and it has to be a discrete amount of energy, and I can bump it up into a higher level of energy. However, the electrons don't necessarily like to be at that higher level, and they will cascade down to lower levels, or lower shells of energy, and when they do that, they lose or they release the energy that was given to them, and that energy is released in the form of light, or a photon. So going along the lines of that, I just have a pretty horrific drawing, actually, but I talked about taking hydrogen, exciting it by putting across a electrical potential. It gives off light. I take that light, the light goes through the prism then breaks the light up into its individual wavelengths, and what I end up getting is these different lines. And for hydrogen, the visible light that I can see, the lines I can see, if this is all kind of black strip, I get 4 distinct lines of color. I get a red line, I get a light blue line, a dark blue line, and then way over here a violet line. And these 4 lines are known as the Balmer series. They're named after a gentleman by the name of Balmer. I believe he was from Switzerland, died in the late 1800s, and I believe when he was 69 or 70 years old, he was actually a school teacher and a mathematician. He came up with some formulae that qualitatively explained these visible lines, these emission spectra. So that's why they call this the Balmer series. And so what I'm going to do is I'm going to start here, and what I'm going to try to do is I'm going to try to prove the theory that I presented to you earlier, that this in fact works. And I've got to show people the money, and hopefully anybody with a scientific mind, anybody who wants to look at things objectively would say, hey, that's a great idea, it sounds nice, but give me some proof. And so I'm going to start doing that. So let's just go ahead and draw an energy level, and we'll just imagine that the nucleus of our hydrogen atom is down here, and this is the lowest level of energy, that's n equals 1. And then the jump from n equals 1 to n equals 2 is actually a really big jump. It's a really big jump to go to n equals 2. And then from n equals 2 to n equals 3, it's not a particularly big jump. And then from n equals 3 to n equals 4, it's even less of a jump. N equals 4 to n equals 5 is even less of a jump. And we'll go to 6, even less yet. And this, of course, continues on and on and on ad infinitum. So, this is what we have going on here. We have our different energy levels, our shells, if you will. And when I look at the light that's emitted from this hydrogen, so what we're doing with the hydrogen is we're putting electrical potential across it. It's exciting the hydrogen. The electrons are being bumped up to higher energy levels, and then as the electrons fall back to lower energy levels, they release this light that we can be seen. And that's what we call emission line spectrum. Now, this light that we see, the wavelength, as we talked about in the last video, red wavelengths are longer, lower energy. Blue wavelengths are shorter, higher energy. The energies of these individual wavelengths of light had better match what this model, what this atomic model suggests, right? That's our proof there. Is if this model, if we can get this and this to match, that energy to match, because we're talking about discrete amounts of energy, then we have a winner. So, what we found is, through experimentation, through the mathematics, is that if I have an electron that is in the 6th shell, and it falls down to the 2nd shell, this wavelength of light is predicted. So that means that if I excite an electron up here in the 6th shell, and it were to fall down to the 2nd shell and give off a photon, it would be this violet short wavelength photon. And lo and behold, the model does predict that in fact the energy difference between 6 and 2 is exactly the energy that this violet wavelength of light has in it. Now, let's just go ahead and continue over to the dark blue line. If we go from 5 to 2, so if I'm here at 5 and I drop down to 2, the photon that is released, the predicted amount of energy is exactly the amount of energy that goes into this dark blue line. Okay, and if I have, let's see here, a 4, and that electron were to lose energy and fall back to the n equals 2 state, the energy predicted would equal this. And if I had 3 and it were to fall down to 2, the light released would be in that red wavelength. So in fact, the Balmer series are predicted. We can predict exactly the exact amount of energy in the light that we see in the Balmer series. Does anyone, however, see a problem or a potential problem here? We've got this nailed down, but we know that in a normal hydrogen atom, in the ground state, where is the electron? Well, the electron is way down here in n equals 1. Why do we not see any light? If my electron starts at n equals 1, I should have at least some electrons and some atoms of hydrogen going from maybe 6 to 1, or maybe from 2 to 1, or from 3 to 1, but I don't see those in the Balmer series. And is this a problem? Well, it potentially, but what is actually happening is this jump from, say, 3 to 1 is a huge jump, because there's such a big difference between 1 and 2. And in fact, the energy released, the photon released, has such high energy that it's not visible light. It is in the ultraviolet wavelengths. So in fact, it is being emitted. The human eye just can't see it. See, the Balmer series is all visible light, but these high energy photons being released from those transitions into those from higher to the ground state, those photons are such high energy in the ultraviolet range that we don't see them. So there we go. We'll add another piece to our puzzle of light. Thanks for hanging in there, guys. Take care.